guys, and welcome to this video about deriving exponential functions. So what I've got here at the moment, accidentally press that button a bit. Okay, what I've got here is using Graphmatica, and I've drawn in the exponential function, so y equals e to the power of x. Now, in this particular section, we're not going to do a formal proof of getting the derivative of the exponential function. We're going to use this piece of software to essentially show what the derivative would be equal to, but it's not a formal mathematical proof. Okay, and it's going to be extremely simple to do that. Just take a look at that colour there. That's the sort of purpley colour, that's the original function, and here on Graphmatica is a very useful little tool which will graph for us the derivative. So keep an eye on this. So let's derive. Okay, notice the colour change there. So what does that mean? What it means is that we've found the derivative and it's equal to itself. So let me just swap over to using a little bit of pen tool for a moment. So guys, what we've just been looking at with Graphmatica there was, if we have our, let's get that tool back up, we have our exponential function, and we just graph that. What we're seeing is that the slope at any point, in other words the derivative, is also equal to e to the power of x. So yes, it means that if we've got our good old exponential function, and I wanted the slope, say, at point A here, and let's say this was corresponding to an x value of, say, 3, and this of course would be e to the power of 3, because that's what y is equal to, e to the power of x, then the slope at that point would also be e to the power of 3, which is a pretty remarkable sort of result, but there you go, that's what the result is. Okay, so we have something that we can now use to get the derivatives of other exponential functions. Now, let's take a look at an example of what I'm talking about. So let's take a look at, say, this quite simple sort of result. Let's say we had y equals e to the power of 5x. Now how would we derive that? Well, we have this result, that the derivative is equal to e to the power of x. And we also have something called the chain rule that we looked at just on Friday. And the essential result of that was that if we had y is equal to one function put inside another function, that the derivative of that was going to be the derivative of the outer function times the derivative of the inner function. And there's also Leibniz's form, which sometimes I prefer, but we'll just leave it with Newton's one here at the moment. So how would we sort of use that with this one here? Well, what we've got, we actually have here a composite function. We could imagine, for example, if we call, okay, y equals e to the power, let me just put that out, come back to this just a moment. So just back here again, guys, I've just done a little bit of work here on the left hand side. So let's take this, just work through this example here. So we've got this exponential function, which is a composite function. Okay, so let's imagine function g is that 5x. Okay, and so function f is that e to the power function. Okay, so e to the power of function g. And according to the chain rule, it would be the derivative of our outer delta function, so the derivative of e to the power of g, okay, which would be itself times the derivative of this e to the power of this 5x, I should say, which is just 5. So when we put those two together, so it'll be e to the power of g times 5. So 5 times e to the power of g, and replacing g with 5x again, we get back to this point here. Okay, let's take a look at a further example and try and perhaps streamline this process a bit. So let's take a look at, say, the situation here. Oops. I don't need one that's an exponential, of course. Okay, so what we've essentially got here is this is once again a composite function where we've got 2x plus 4 has been put in place of that e to the power of x. Now, I'm going to use as Leibniz's notation here because I find this a little easy to explain. So we're after the derivative of y with respect to x, and using Leibniz's form of the chain rule, the derivative of y with respect to u times du over dx. Now, where is u? Well, I'm going to make this substitution. I'm going to let u equal 2x plus 4. So this would become y equals negative 3 e to the power of u. Okay, so according to Leibniz's form of the chain rule, we derive y with respect to u, which is pretty easy to do, I hope. And we're going to derive u with respect to x, which is also pretty easy to do. And then we're going to multiply those two together to get our result. So let's just go over here somewhere and let's put that working. So deriving u with respect to x would just be 2. Derive y with respect to u. Okay, well this is just the exponential function. The derivative of e to the power of u is itself times negative 3 in this case. So negative 3 e to the power of u. Okay, so it basically is itself. Putting those two together then, dy over dx is this result here times this one. So negative 3 e to the power of u times 2. So that would be negative 6 e to the power of u. And let's replace that u back with this here, the 2x plus 4. Okay, so that was pretty good. Can we streamline that at all? Yeah, probably. Notice that the derivative of this was just 2, and then we were multiplying that with the original function. That happened up here. The derivative of that is 5, and we end up multiplying that 5 with the original function. Okay, so maybe that's a little bit of a shortcut we can do. Let's try one more example. Let's go to a new page, make a new page. And so if we had another example, let's take one that's got a bit of a fraction look to it. 2e 5 minus 4x over 7. Well, that would be the same as 2/7 e 5 minus 4x. Okay, and if we did that shorthand approach, I reckon the answer would be the derivative of this here, which is negative 4 times our original function. Okay, and that would be that, which would give negative 8/7 e to the power of 5 minus 4x. If we just check that with using Leibniz's approach, y equals this function here. Let u equal the 5 minus 4x, and du over dx y would become 2 sevenths e to the power of u, and dy over du would be that 2 sevenths e to the power of u, derivative of e to the power of u being itself, times our 2 sevenths here. So putting those two together, dy over dx equal to dy over du times du over dx. Putting those two together, we get our 2 sevenths e to the power of u times this negative 4. Now that's negative 8 sevenths e to the power of u, and putting u back in terms of x, which was this one here, 5 minus 4x. Okay, and that's the same answer as that one, except this was a lot less work than all of this. So I would recommend that we make this conclusion: if we have some number e to the power of some function of x, that its derivative is going to be, well, looks like the derivative of this, so f dash x times our original function. Okay, and that looks like a lot shorter way of doing it than previously. Okay, so that's it guys, we'll catch you on